our speaker today is Vincent himself. Okay, he's a data analyst and scientist, and he fights for internet abuse with ML at Google. He uses advanced learning and software engineering to protect Chrome, Gmail, and Android users against phishing activities or attacks, which potentially steal millions of dollars every week. So he's also a writer for Towards Data Science Medium, so look that up. It's to guide aspiring MLs and data practitioners with 500K plus viewers globally. Okay, so his talk is on convolutional neural network, or in other words, CNN. He will talk about the basics and the use cases and techniques using the dogs versus cat image classification. This includes CNN's rules, CNN's regulations, technique dropout, and image augmentation. So by the end of this talk, you will understand the institutional CNN mechanism and implement a simple classifier on your own. Okay, guys? All right. Okay, Vincent, over to you. So I'm just going to close our camera.
Okay. All right. Okay, I hope I'm sharing my screen now.
Yes, you are.
Okay,
I'm just going to
cool.
put myself on mute so that I give the floor to you.
Okay, cool, perfect. All right. Yep, so hi everyone. I know that this is after lunch, so I'll try to make it as much engaging as possible. But then thank you so much for coming and listening to me. As what you know, I'm going to present regarding introductions to convolutional neural network for image detections. Right? But first of all, allow me to introduce a little bit of myself. Yep, so my name is Vincent. I'm a data analyst doing machine learning at Google. So in case if you want to engage to me after these presentations, feel free to take a look at my Medium articles, LinkedIn. I try to be as much reachable on LinkedIn as much as possible, and data podcasts as well. Right? So just a quick disclaimer about these presentations is that this is based on my own views, thoughts, and in no way is related to my employer, organization, committee, or any other groups. So just a quick intro about what I'm doing at Google. I work at Trust and Safety Department to prevent phishing at scale with data analytics and machine learning. So how is this relevant to computer vision, right? It's because that, let's take a look at some phishing example, right? In this case, it's a Facebook phishing. You know that it looks like Facebook. It seems like quite legit, but then when you take a look at the URL, www.sanagutisturismo.co, we know that it's a malicious website trying to catch your identity. So what we do, our product is called Safe Browsing, is that we try to make sure that you don't get scammed and phished. So what we do is that we are going to blocklist it and then show you these red interstitial warnings, right? Like to show you that you shall not pass. Okay, like the Gandalf, right? So in this case, I use computer visions because for very simple reasons. We know it's a Facebook phishing because it looks like Facebook, but it is not Facebook, right? So the looks like part is where computer vision can come in to identify whether it's a phishing or not, whether it's a malicious or not. So that's why this kind of technique is something that I'm really interested to learn more because it is really, really useful for image classifications. Right? So if you want a bit of summaries, this presentation is also based on my Medium article, Understanding CNN, that I wrote last year. And there's a collab demonstration, but for the sake of the time, I think I only have like 20 to 30 minutes. I'll be skipping the collab demonstration, but I'm going to explain to you a little bit regarding the codes. Okay. So this is the today's agenda. Bear in mind, it's a lot of things. There are a lot of contents in these presentations, but I'll try to make it as condensed as possible, while at the same time making you interested and excited to learn more. Right? So the first one, I'm going to talk about why we need machine learning in image recognitions. Right? The second one is that I'm going to talk about the CNN as a technique, deep learning technique for you to recognize images using convolutions, review activation functions, and max pooling. So I'm going to speak briefly regarding these techniques. Then after that, the third one is regarding the CNN flags. So by the end of the day, what you care about is that you might want to classify, right? In the multi-classes classification problems, such as like identifying horses, cats, and dogs, you want to have those probabilities, right? You want to have those sigmoid-like probabilities, like how much the probability of it being cats and dogs and getting the values of the stacks. And the fourth or fifth is basically more towards how you can improve your models by avoiding overfitting, and finally transfer learning using the pre-existing model. Okay. I hope that by the end of the presentations, I will have like 5 minutes or 10 minutes for Q&A, depending on what time that we are finishing, until 1:45. Okay, if we get a big picture about what we are going to do today, let's jump into it. The first one is related to machine learning in image recognitions. So why do we need machine learning in the first place, right? The first thing that we need to take a look at is that image recognition is hard. And what I mean by that, in this case, I did search for the word cat on Google search a couple of, I think last year. And this is what it returns to me, right? Based on what we can see, there are only like 3 legitimate cats that we can see like on the pictures. The rest is more like the cat's Broadway and even the cat's graffiti. And it's very hard for us in this case, right, to identify whether these are really a cat or not, even for human beings, right? So now the problem is that how do we teach our computer to look at whether this is a cat or not, right? Let me give you an example of like having this black cat as a picture, right? As a classical programmer, you are going to create a feature, like for example, oh, a black cat is a black color and has sharp ears. Sorry. And so what you do is that you can cut it in a horizontal line, and after that you color histogram to identify whether it's a black or not, right? You can do like majority colors percentage of black, and you can do like in color histogram whether there's a certain regions, then you can identify sharp ears, right? And then you say, yeah, it is a black cat, right? By doing a certain threshold classification. But then, let's say I give you a second image, which is a cat wannabe, right? It's a dog that wants to be a cat. Now, you might think that, hey, according to these features, this is no longer a cat, right? So what should we do? We might want to increase the number of filters and features that we want to introduce. Let's say maybe the ears, maybe like no longer the ears, but maybe the eyes and the nose. The nose should not be very broad. The eyes should be like a bit white in color. But then, if I were to give you a more complex, like Siamese cat, Burmese cat, then suddenly you need to create more filters, right? More features out of that. So what we need is an automatic way to determine critical features to identify other objects. So this is the problem statement. How do we determine the feature scalably, right? So welcome to why and we are going to talk about these techniques. But in that ECN is actually so that's
Back? Can you hear us?
Yep, I can hear you. I think I got kicked out for some reasons.
I think it's the internet connection. Sorry about that. Okay, hang on, yeah. We'll
Okay,
get you back up on screen. Okay.
okay. All right. So,
Yep.
what do you see? Young lady or grandma or both? Okay. All right. Since we don't have a chat here, so I keep going. Okay. So this is a painting introduced by Edmund Boring, which is a psychologist that is called "My Wife and My Mother-in-Law" painting, right? But the figure seems to morph from young lady to old woman. And you might be able to see the bounding box here, like which is the red color here. So these boxes determine the features, the objects that how you would classify. So maybe like if the first thing that you might see is the curve, which is at the middle, then you might see that it's a old lady or a young woman. It's an eyes, right? And there's a joke here. They say that if you are younger generations, then you will more likely to see it as a young woman. Why? It's because that you are used to looking from images from left to right or bottom to up. Imagine Instagrams or imagine like like swiping motions on like applications, right? But if you're like older generations, then you will see the picture from the top to bottom, right? So they will see the eyes first, right? And if you're older generations, then you are more used to like reading newspaper, for example, compared to playing with Instagram or Facebook. So basically, your interpretations, whether you think if this is an old lady or the young lady, is determined by two things. The first one is the data itself. In this sense, it's strokes of the painting. The second one is prior knowledge. So your scrolling habits will identify which features that you might take a look first. And even your understanding of faces might actually cause you to identify this picture differently. For example, like, all the cartoons like Ugly Betty or even like Popeye and even like the Adventure of Tintin, is always like featuring the small eyes, right? So you were more likely to see this as a small eyes compared to nowadays we have animes and mangas, which always the eyes are very big, right? For me, my eyes are very small and people will say that, right? So in this case, your prior knowledge of whether like your understanding of faces will actually affect whether you will see it as a certain object or not, your prior knowledge. And combined with data and prior knowledge is the features, which what we want to identify. So this is what we see. Biologically, this is how we identify images and objects. Okay. So how does computer see? Right? A computer doesn't see like us. It doesn't see the stroke of paintings. But what it sees is a group of pixels. Right? So black is 1, white is 0, and basically from the top here, you can see there's a curvy motions, which means that it's a black. But the bottom one is a horizontal line, which means it's a choker or mouth. That's what the computer sees. Right? But how does we form a prior knowledge on top of computers is why we use convolutions. Right? So in this case, it's very simple. Convolutions is a very old technique. In fact, it's very used more often in the image manipulation, such as Gaussian blur, or even like like Instagram filters, such as embossing and creating all of those stuff, right? So in this case, if you take a look here, we have a certain like 3x3 array, sort of like a matrix, and after that, you can see that it forms a horizontal line with 0, right? So if you apply convolutions into the raw image at the bottom, it will become the image on the right, right? So what does it do? It identifies horizontal edge, right? So it's for edge detections for horizontal. So how do we actually detect edges and patterns from convolutions? It's actually very straightforward. So let us understand from 1D convolutions, right? And I have a simple question here. Which order of the element where I see there is a change from 1 to 0? Okay. The simple answer is this and this, right? So you know that the element of 3 is like, that's where the changes is made, 1 to 0. So how do we detect it with the convolutions? It's also very simple. For example, we have another like ND array, which is like 1 times 2 kind of array. And then after that, we use a window So imagine there's a slider here, the window, which only opens two elements from the ND array, right? So in this case, we open the left elements and the right elements, and then after we do dot multiplications and sum it up, then after that it will become a 0, 0, 0, 1, and 0. So this is the end result you get, right? After you combine all of this. So notice here that this is very interesting because the fourth element, once we do the multiplication and dot product is no longer 0, right? It's like 1, right? And the rest is like 0. So that's where we know that that's where a certain feature happens, right? And the best thing is that this is a very value and scale invariant. What it means is that let's replace 1 to 5, right? Or replace 0 to like -1 or something. Then the results, the end results that you see will not change. It's like 0, 0, 0, 1, 0, right? Because what we care about is the left value and the right value is the same. Apart from that, no matter like what's the scale of the value is, I will return these end results. So it detects the patterns nicely. Okay, this is convolution 1D. We can implement it with 2D, right? We do the same thing, but except it's 2D array. So we have, let's say, inverted phi, like greater than signs, and then like we have the pixels of those, and then we give a certain kernel. The kernel is like number 5 on a dice, or it's an X, and after that we do the operations. So what it does here by feature maps, the output is that you can see that where the diagonal happens. So this is a diagonal case detection, right? So the inputs here is the data. The kernel here is the prior knowledge. And the IK here is a feature map. So what it means using data and prior knowledge to identify a certain feature, right? This is how a computer sees and how it actually mimics how we see as well. Apply it again to the RGB and it's even clearer. You will have like 3 stacks here for the non-black or white kind of images. And by the end of the day, you will have like 3 different feature maps that are stacked on top of each other. Okay. So that is convolutions. Convolutions help us identify features from data and prior knowledge. Right? The second part that I want to talk about is the ReLU. So in terms of activation functions for ReLU here, I'm not going to speak very detailed about this because I don't think I have time. But then what you want to see is that this is actually used in artificial neural network. What it does is that it's very simple, right? So you can see if it's below a certain threshold, then it's 0. If it's above a certain threshold, then the gradient is 1, right? So this is very simple and also adds the nonlinearity functions. And because of the stability of the gradient also, this also reduces the vanishing gradient problems, which are actually seen in a lot of like sigmoid kind of like activation functions and so on. But what I think this is very interesting is because it works really well, even though it's simple. And I think it kind of mimics the biological understanding of how we perceive pain. For example, let's say that we just touch our skin like this. We just touch our skin. We don't think about it as a pain, right? We just have the touching sensation. But let's say that if I apply pressure, like from 0 to like very minimum, I keep adding it, I keep pinching myself, right? There's a certain threshold in our brain that we register it as a pain, right? So I think this is what ReLU is sort of like kind of doing. It kind of mimics what we have in our brain. Okay, and it works really fine, and it's very simple. So this is currently what I think, based on experiments and based on like trial and errors, what computer scientists have said that this is really working well. Okay. The third technique that I want to explain is regarding max pooling. So max pooling here is very simple. Imagine you have the feature maps from the convolutions. So you did convolutions already. And what you have is a 4x4 as a feature maps inputs, right? Then after that, what I want to do is that I want to divide this into 4 regions. So you do a sort of like 2x2 kernels, and after that you slide it with strike 2. In this case, you can do strike 1 as well, but strike 2 meaning that I jump by 2, right? So that's why he can split it like quite cleanly like this, right? And based on this each region, we want to take the maximum, right? So in this case, the red will return 6, the green will return 8, the yellow will return 3, and so on and so on. So why do we do this? You might ask. There are 3 particular reasons why. The first one is that we want to remove external details, right? So what I mean by external details is that imagine the Edwin Boring painting just now. What we care about is where the ears lie, right? We don't really care about what the hair of the woman is, or we don't really care about the background of the woman, because it is external detail. It's something that we don't need to keep in mind for, right? So by doing the max operation here, basically we just take the areas that our prior knowledge, and that also reduces overfitting. Okay? The second one is, of course, taking care of what's the most important. It just takes whatever is important and then leave it be. The third one is regarding the computational values and also like efforts that are needed to do like subsequent operations. For example, in this case, very simple, 4 times 4 to becomes 2 times 2. So what it means is that from 16 to become 4 sort of like features, right? For values, right? So what it means is that 75% reductions in computational efforts. And this is actually particularly relevant to us as well. So let's say that yesterday you saw a very cool car, like a Ferrari red car, and then you know all the details about it. Yesterday you know all the details, you know like how the steel work, how the steel looks like, how big is the windows and whatever, because you're very interested in Ferrari cars. Okay. But then if I come up with a question that asks you, do you still remember what the driver is wearing? Or do you still remember what's the house behind the walls and the fence color is? Then you're like, no, I don't remember. Even though you have the vision that should enable you to answer that questions, but you don't remember. And what happens here is just we only care about our prior knowledge, what we think is important, which is the car, because you are fixated on the car. And then you take the details, what's important about the cars. The rest, you just leave it be. And this is how our brain actually works with visions. It especially removes the degree of the information overloads. So you just keep whatever that's important, and then you keep it in your long-term memory. Okay, so this is mimicking what we do in our real life as well. So just a quick recap. This is the core techniques of the CNN and the most important of this presentation. The first one is convolutions, understanding what's the features from your data and then the prior knowledge. The second one is review activation functions, introducing non-linearity in order for you to represent a complex reality. And the third one is max pooling, only caring about what's the most important so that you can reduce information overload and you can proceed it with minimum computations burdens for your deep learning frameworks to work. Okay. So the third one is that we want to understand how we receive value from it. CNN stacks and fully connected layer. Okay. So this is the CNN stacks and fully connected layers. So as you can see that by the end of the day, by the end of the convolutional neural networks, then we want to put it in the FCL, fully connected layers. And what FCL does is that it's very similar to ANN, which is artificial neural network. So you just like flatten whatever that you have on the 2D feature inputs into become 1D. And then based on that, you will run an artificial neural network that's all fully connected to each other, right? As simple as that. And by the end of the last layer, it will identify whether maybe a certain neurons that fits your multi-classification problems very nicely. Okay. So this is the CNN stacks of a bunch of convolutional 2D and max pooling alternatively. So you can see here that the more layers that happens by the end of the day, in this case level 8, you can see that there is more discovery of more complicated patterns. So maybe the early stage of the layer will just identify a certain edge, 2 dots combine together to become a line, but then the second one will identify a curve, a pattern, and then the third one will identify a texture, right? So by the end of the day, it becomes more and more deep. Okay? So this is what Conv2D and max pooling does. And as you can see, max pooling here is reduces the size by half. Okay. And this is another activation layer functions, which is a Softmax. So what Softmax does is that, let's say that you care about multi-classification problems, cat, dog, and horse. So what it does is that squash all the probabilities. Remember that neural network is a sigmoid on steroids, right? So it will give a probability, no matter what, it will give a probability. And based on the softmax magnification functions, what it does is just squish it into one, right? So in this case, you will see that the first image is a cat image. So it's a 0.71. The second image is 0.98 for horse, but the third image is 0.49, 0.49. So it's not sure it's cat or dog. So it gives a very nice representations of like how you think this image represents on top of what we have in our multi-classification tables. Okay. So this is just a quick big picture. So we have cats and dogs, and then we put it into input layers. We activated all the neurons, and after that, by the end of the day, we have output layers. So these are the codes that I want to put it inside the, actually I put it inside the collab, but I'll just be very brief about it due to time restrictions. So we use TensorFlow and Keras. TensorFlow is a deep learning library, and Keras is an abstraction layer on top of that, right? And after that, we use a bunch, we import a bunch of like libraries in order for us to get started with the CNN. So this is a very quick CNN structures. So you can see there's a CNN stacks layer. So you put like Conv2D, max pooling, or you can put any other like layers that such as dropout and so on. Then after that, by the end of the day, you connect it to fully connected layers, which like sort of like flattened maps of like feature inputs. And after that, you it trains on top of each other, do the backprop and feed forward, similarly to ANN. Then after that, just like how you do additional network, you compile it, you put the loss there, loss functions, binary cross entropy for sigmoid, category cross entropy for softmax. Okay. Right. Oh, sigmoid means that whether it's a dog or what is the probability whether it's a dog. So 0 to 1, but softmax is basically you have multi-classification problems. So you have what's the likelihood of it being a dog compared to cat, what's the likelihood of being a cat compared to dog. Basically, there's a comparisons in softmax. So we train our CNN, and this is what it gets, and this is the results. So you see that some of those are classified correctly, and some of those are not. So after that, we take a look at the results. It seems that something is wrong here. So this is a sign of overfitting. And the reasons why you see that there's overfitting is because the blue color here is actually the training accuracy. So the training accuracy supersedes the prediction accuracy. So what it means is that the model is overly complex. It does memorization compared to generalization, right? So this is what it means. Okay. There's a teachable machine as well if you want to understand and train CNN directly. So teachable machine from Google is a very good site for you to actually train rock, paper, scissors directly from your laptop camera. Okay. All right. So I think I only take like 5 more minutes before we move on to the Q&A. I think we start later, but then feel free to let me know if you have more questions or if you want more understanding regarding the sectors that I might not have time to explain on. So this is avoiding overfitting, right? So how do we improve our models? So there are a bit of common mistakes, but 2 notable ones is that there's over memorizations, and also the data set is relatively small. So we need to know that neural network is very complex because it's a bunch of like black box, right? Because you have a bunch of layers, and then like the more layers it is, then it will be very, very complex. And usually, if you don't have much samples, it will be very biased towards a certain sample in a certain classifications. So that's why your sample data needs to have a lot that represents the production reality. So in this case, let's say that I have one image at the dock here at the left. I will do data augmentations. So what I mean is that I will do a bunch of manipulations such as zoom, crop, flips, and whatsoever, so that from one image, I can make it into 4 images. From 100 image data, I can make it into 400 images data. And this is just a quick way for you to get a sample by using the resources that you have. Okay, to implement it, very easy. So you put an image data generator, and then you put it into the Keras TensorFlow library, where you are identifying the trained data generator. Okay. The second one is dropout. And how dropout works is that it removes the complexity. It's a regularization technique where you just like shoot neurons to death, right? You just shoot neurons to death randomly for each training steps. So from the left here, which is like all neurons interact with everyone in the previous layer, it becomes into something that only a few neurons interact with a few neurons on the previous layer. And it's randomized for each training step. And this is really important because it prevents the conspiracy. You know that if you go to a bank, right, for example, most likely you will interact with different tellers, right, every day. You will interact with different tellers, different tellers to on a shift at any given week. So they will have
Hi, Vincent. Yeah.
okay. So
Okay, you're
I
back.
think we can go to Q&A. Yeah, because like I think only have like 3 minutes left. Yeah, but the idea is that I want to say that transfer learning actually improves the accuracy a lot.
Yeah. So far,
Yeah, so this is the charts of the transfer
yeah.
learning. Okay, so I know we don't have much time, so can we have like maybe like 2 questions?
Box. Okay.
Yep, yeah, still more, but okay. I think let's end it here.
Maybe you check on your chat box.
This one.
There's a question on your chat box. Yeah.
Okay.
Can you see it?
Yep.
Yeah.
Okay, let me read it in case like you want to listen. Okay, since you are a data analyst or scientist, I have a question since data analytics is new here in Brunei, and I am from UTB as well, taking it as a course as a 3rd year. What are the things I could look up into in relations to data analytics? Okay, thank you, Aviva, for saying. So let me try to rephrase here. So I guess like what you like to know is that what you could learn in terms of like career and learning tracks. Okay, I would say based on my sample size, which is 1, it will be like to know first about like data analytics in general, right? So maybe you want to try like to know like classifications and regressions, supervised, unsupervised learning, and so on. And then once you know like the general, how you do EDA, exploratory data analysis, then you want to go deeper, right, to how exactly you implement on the machine learning. And then afterwards is deep learning, which is what I presented today. And afterwards, you might want to know to how you can use it to solve the business problems, right? And of course, like if you know like applications like Gojek or Traveloka from Indonesia and Grab, then you will need to know about ML operations. So ML operations is like software engineering, we call it the DevOps, but including the data environment ecosystem. So there are a lot of things that you can think about in terms of analytics, but I suggest try to look at like what problem you can solve with the simplest ideas as soon as possible, and dig deep into deep learning once you see there's a strong use case for you to look forward into it. Maybe like computer vision or NLP. Yep. I hope that's good. Okay. All right.
Okay, she has a question.
Yeah. Second questions and the last.
Yes.
Okay.
It's just a question you're used for image processing. But what about sounds? I heard that you can use convolutional neural networks to help detect words as well in audio clips. How does that work?
Oh, okay. All right, so, no problem. Okay, so how? So let me rephrase. So basically, how do we use CNN for maybe like other stuff, like for NLP to identify patterns in words? And the idea is that yeah, you can, because when we talk about NLP, we talk about the context, right? For example, I go to a bank right? The bank can be a river bank, or the bank can be a financial institutions, right? But if I give you like a previous sentence, like for example, I need to invest, I need to open a bank account, right? So that means the bank is the financial institutions, not the river bank. So the idea of convolutions is that it identifies a context, right? It identifies the pattern inside a sequences of data. So in NLP, the data, unlike the image in pixel, but the data is tokens, right? So you can tokenize the words, and then you can put it side by side in sequential orders. And after that, you use the convolutional neural network, or like a convolution in general, to actually represent the sequences of words one by one. Okay, like one region. And by the end of the day, you can do similar like operations, to find, for example, like sentimental analysis, or if you want to find out the semantic meanings of this bank, then you can do that as well. So that's how you use it. Okay, I think we have more time.
All right, thanks a lot, Vincent.
Just a quick sum up is that feel free to reach out to me. I'll try to be contactable in LinkedIn. And there's a survey as well. Please give me your feedbacks on how I should do better to present or to explain about these concepts. Thank you so much. That's all from my side.
All right. Thank you very